I must tell you that since the time of Planck, there is something called, this is what people call as black body radiation. We had talked about this earlier, and so essentially, if you have energy density of mu versus mu, it has got some kind of a behavior like this, and this is universal. This is universal curve that defines only on temperature. Only if you change the temperature, the curve will change. Otherwise, this for a given temperature, the curve is fixed. So this is so we have seen that Planck's work has shown that this u mu t is given by 8 pi mu square by c cube into h mu divided by e to the power h mu by k dt minus 1. So this is called Planck's distribution. Now you can see I have wantedly written it in this fashion. So this particular factor is called density of modes, okay, and this particular factor is average energy of a dipole oscillator of frequency mu at temperature T. Of course, in deriving this, we have to assume that so Planck had assumed that the oscillator can emit or absorb energy in discrete packets or quanta whose energy is given by H. So with this assumption, we have already seen as an application of our canonical ensemble that you can derive this as the average energy of the system, and this is density of modes. So density of modes is defined as that if you have, that is, so this was derived in two different ways. So for example, Planck had used, so this part is clear. This part is, this also was derived by differently by different people. Planck has used an argument which is similar to microcanonical ensemble. Later we have shown that Lorentz has used the canonical ensemble, and different people have used different statistical techniques to get this average energy. Now this one was density of modes was derived by two people. I think initially Planck had derived this. So Planck had shown that this U of mu comma p is equal to 8 pi mu square by c cube into average energy of the oscillator. Okay, so this was done by Planck, I think in 1898 or 97, 98 or 99, something like that. Enumeration modes. You can ask the question that if you have dn, which is defined as the number of stationary modes, stationary waves in the frequency range from mu to mu plus d mu. Okay, if you define dn like this, then you can write down dn is equal to some g of mu into d mu, right? And then he showed that this g of mu is equal to 8 pi mu square, 8 pi mu square by c cube. So this is another derivation. So why I am telling you that these two different types of derivations is that Bose had first realized that so some of the starting points of Bose is that he noticed that the derivation of 8 pi nu square by c cube factor is by using classical electrodynamics. By using classical electrodynamics in all the attempts till this time. Whether it is the work of Planck or work of Rayleigh, this argument is classical argument. So Bose realized that if you are talking about a quantum mechanical or a quantum result or something which is non-classical, then a part of it should not be derived by using classical electrodynamics, and the rest of it, a part of it is using the ideas of quantum or ideas of quanta and things like that. So the first thing that he noticed was that this is like a kind of hybrid approach. But everybody who developed this formula of Planck's formula after Planck, including big names like Einstein, Debye, Lorentz, etc., they all have used either Raleigh's argument or Max Planck's argument to fix this prefactor, and all others have been only trying to derive the second part, that is average energy part, differently. Now one has to understand that this formula, is so you have this average energy, right? So this average energy is energy of the dipole oscillator. Now, what is this dipole oscillator? Dipole oscillator is so dipole oscillator is basically, it comes from the material. Okay, so that is it is a part of the material with which the black body is made up of. But I think Bose had definitely slightly deeper understanding about it, because suppose, let's say that you have some black body here. Okay, so let's say this is your black body. Okay, so and then it is emitting radiation. Okay, so this is radiation. Okay, so now let us look at some. Let's look at some volumes specifically. Let's concentrate only on this volume where we have radiation, but there is no black body. Okay, in this you have only radiation. Now, can we talk about thermodynamics of radiation, independent of whether this is given by a black body or can we forget about this source? Now, suppose if you want to talk about statistical properties of this radiation, then where is the dipole oscillator? Because in this region I have radiation, but then I cannot talk about any dipole oscillator. So even though this idea of radiation as a thermodynamic system was somewhat somewhat being considered by Max Planck and others more seriously, but I think a deeper question about it was, in my opinion, was definitely asked by S.M. Bose, in which he said, okay, so what is this dipole oscillator? Now I want to only consider radiation as a system. No, I have radiation, that's all. There is no, I don't know whether, now since that radiation is basically a universal dependence on temperature only, now whether I have black body of material 1 or material 2, it doesn't matter. If that is the temperature at which it is emitting that radiation, and I have only radiation here. Okay, so I have radiation at some temperature T, that's all. Now, I should be able to derive this expression by considering just the radiation without considering any dipole oscillator. So, is it possible to derive the whatever Planck's radiation formula just by considering the radiation itself? This is, I think, the question which I think Bose had asked. I do not know whether historically what I am saying was the question, but this is at least what I am appreciating what would have been the question. And I think this also tells you that Niels Bohr had used an interesting Niels Bohr used a kind of a term like this. He used a term called temperature radiation. Okay, I think he was using this name for black body radiation. So there seems to be some understanding in Niels Bohr's writings that he also felt that radiation should be taken as an independent quantity. One doesn't have to always link it to a black body. So temperature radiation is a word which Niels Bohr used in his papers, which essentially means that you should have a system radiation at that temperature. That's all. So this is these are the two aspects. So the first aspect is related to the first part of the formula, namely 8 pi nu square by c cube, and the second one is related to the second part of the formula. So I think these two things have led Bose to look at this problem more carefully, and the success is that he actually solved both of them in quite different way and was able to derive that expression without considering the process in which others have derived. And in some sense, we can say now that this derivation of Bose turns out to be the most fundamental derivation of this black body radiation formula. Okay, so now let's look at the first part. Okay, so let us discuss the the way in which Bose has derived. So let us first talk about Bose derivation of 8 pi nu square by c. Now, remember this, whatever we are talking about is something like June of 1924. June 1924, Bose wrote this paper. So I must also tell you this is before Heisenberg are showed in this. That means our basic quantum mechanics was not formulated. So old quantum theory was there, but this is before Heisenberg has shown it. So the new quantum theory is not there. Now you can say that there was an understanding that Einstein in 1905 said that radiation exists as, he called it as light quanta. Light quanta, and energy of quanta is given by E is equal to this. So this is something which Einstein had shown in 1905, and Niels Bohr had used it later in explaining what is called the spectrum and things like that. And a year before this, I think Compton had done this experiment where he showed, I think this was in 1923, that the light quanta has a moment. So only when you consider light quanta to have a momentum, E that is equal to h mu equals. The Compton effect, what you observe in Compton effect can be understood only if you consider that it has got a momentum h nu by c. And then you consider the momentum conservation between the collision of light quanta and the electron. Then you can derive an expression that agrees with the experiment, the shift in the wavelength. So this is something which was known. So Bose has taken this seriously, and then he tried to ask the following question: that supposing if let's say that I have even though the name photon came a little later, but Bose has used only light quanta in his paper. But let us try to use it because it is simple. And so we have this word called photon for light quanta. Okay. So now, because you have this momentum, so Bose has said, okay, if it has momentum, so then we can talk about a momentum space. Okay, so let's consider a momentum space. Okay, so let's consider a momentum space. Okay, and let's consider a sphere of momentum p. Okay, and then another sphere of momentum p plus dp. So let's say this is dp. Okay. Now, the volume of this annular region is given by volume of the region between P between spheres of radius P radii and P plus dp in momentum space is given by 4 pi p square, that is the surface area of the inner sphere, into d. 4 pi p square into d. Now, you can ask a question that so we have this quantity. Now, we can talk about a phase space okay, that is momentum space and phase space. But this is basically kind of there is no the energy of the Hamiltonian of the photon is simply c times p. It doesn't depend on position, and hence when you integrate the position of a photon, you will get the total volume of the cavity. Okay, so if V is the volume of the cavity in which radiation is present, then you can say that the number of okay, so let's radiation present, and if h cube is the volume h cube is the volume of some smallest cell in the phase space. In the phase space, then we can ask then the number of cells in the phase space between frequencies mu and mu plus d mu is related to the number of to the corresponding number between momenta p and p plus dp, because P is equal to H nu by C. So you can see that I can write that the number as Dn. Dn is equal to 4 pi T square into dP into the total volume of the radiation divided by H cube. Okay. But now I can write this as 4 pi V by H cube into H nu by C the whole square into H by C into D. Okay. H nu by C the whole square, that is P square, and this is dP. dP is H and C are constant, so it is H by C into D. So this gives us H, here H square is there, H is there, so H cube will cancel away. So I have 4 pi V mu square divided by C cube into D. Okay. Okay. Now, since there are two polarization states, for each light quanta, we have to multiply the right hand side by 2. So we get dN is equal to 8 pi V mu cube divided by C cube into D. So what we have here, so if you can write this as some kind of G nu D nu, we get G nu is equal to 8 pi mu square into V divided by C. And we define G of mu as G mu divided by per unit volume. So that is equal to 8 pi mu square by C. So this is how Bose has derived this chapter. So if you see what is the difference between others and Bose is that Bose has taken this seriously, that momentum is given by this. Once you say that you have a particle and take it as a particle and then do the same analysis that you do for particles. Okay. So if you do it by just counting the number of phase space cells, you are able to get this expression 8 pi nu square by CQ. Okay. So this is the important difference. So you have to simply use this. But then there is a little bit of controversy in the literature regarding this multiplication by 2, because this polarization of an electromagnetic wave is a classical concept, and Bose had set out to work everything from quantum mechanics, but this are non-classical derivation. But this multiplication of 2 it has a classical Okay, so the question that historians have always worried about is multiplication by 2 classical. Now this becomes more important because Bose has always, in his later answers to this question, Bose has said that remember that the particle spin was not known at that time. Okay, in fact, Pauli's paper came in 1925 with the spin and multiplicity, but Bose claims that he discovered the spin. He claims that he wrote a paragraph in his paper relating polarization of electromagnetic waves to the spin of light quantum. Okay, so he claims that he wrote it, but it was removed by Einstein. During his translation. Okay, so this Bose himself has told in some interviews later that he had this one, but it was removed and things like that. But anyway, what we have right now in the black and white is that in the paper he simply gives an argument that it is because of the polarization we have to add this two. Okay, so this is so if Bose is right and if that paragraph would have been there, then the idea of spin would have been also something which Bose would have got a credit for discovering. Because you see that spin, most of you know that it was, as a concept, it was introduced for an electron first, because there was a requirement of understanding periodic table and understanding anomalous Zeeman effect, and through that, the spin as a concept has been introduced first by Pauli, followed by Gauss-Smith and Uhlenbeck. Their work on they are the ones who talked about spin. Otherwise, Pauli was only calling it as two-valuedness, non-classical two-valuedness. That's what Pauli was calling it. And then, of course, a clinching experiment by Stern and Gerlach, where they showed that there is a spatial quantization in the inhomogeneous magnetic. Okay, so these things all were to come. Bose has written this paper. Okay, so this is about that factor of 2. Now, so now if you look at this one, I want you to notice that as I am deriving this, I have not considered the black body, or there is no oscillator anywhere. There's a radiation, and radiation consists of photons, and photons are particles with the momentum, and hence they will have this kind of momentum, and momentum is related to frequency. And then how many, so the cells So here I want you to notice that the phase space cell here. Okay, so the phase space cell is in the modern language is like a state. It is like a quantum state. Okay, it is like a quantum state. Okay, so that is because at that time we don't know there are quantum states, wave function, and all that. So, but now we know a lot of quantum mechanics. So, essentially, when we talk about a phase space cell here, it is the state of the photon. Okay, so that is this part of the derivation.
Sir?
Yeah.
So can you elaborate that dn equal to 8 by v nu cube by c cube? When you wrote it for the first time, like 4 pi p square dpv by h cube.
Yeah. So what I'm trying to say here is that we have a phase space, and we don't care where the atom is. We just I mean the photon is. We just want to know how many how many such phase space cells are there with the frequency nu and nu plus d nu, which is related to this number between moment of p and p plus d, because p and nu are linked, correct? So this is how the p and nu are related, correct? So that is just like our density of states that we used to define. You consider a sphere of radius p, and 4 pi p square is the surface area, and into dp. This will be the volume of this annular region, correct? Okay.
Yes, sir. That is okay, sir.
And that into I don't care wherever it is there, so I will integrate this over the entire coordinates. Then I will multiply that with v. So this much is the volume in the phase space. And now I want number of cells, so I divide that by the minimum cell volume h cube. So that is going to give you the number of cells with the momentum p and p plus d, which is same as number of cells with the frequency nu and nu plus d nu, because I can substitute whatever is p, this h nu by c. Then I multiply lastly by this 2 just to take care of this polarization.
So you're saying you integrated the space part, but you didn't integrate the momentum part.
Yeah, that is because I want this. No, what are between frequencies nu and nu plus d nu, and there is only relation between p and nu. So I have to keep that p and p plus dp, and I don't mind wherever it is in the entire space. So that means I require to integrate over the coordinates.
Okay, sir. Okay.
So that is the first part.
Excuse me, sir.
Yeah.
Sir, one small doubt.
Yeah.
Sir, the volume of the annular region is written as 4 pi p square dt, no, sir.
Correct.
But it will be equal to the volume of the outer sphere minus the inner sphere.
Correct.
I mean, if you do that difference, it won't be equal to surface area into dt, no, sir. Some extra terms will be there.
Yeah, but I think it is somewhat. So what do you get? For example, if you take 4 by 3, you say 4 by 3 pi into 2 plus d3 the whole cube minus 4 by 3 pi dq, right?
Yes,
So
sir.
If we
Some extra,
calculate like that, sir, some square and cube term will be there, and we can
extra
negate
term.
that side.
so you have to keep up to linear in dp.
Yes, sir.
Keep up to
So,
linear in dp.
so it's an approximate value.
Yeah, yeah. So dp square and dp cube you neglect because dp is small anyway. We have to consider dp to be small. But if dp is not small, then you cannot approximate it like this.
Okay, good. Okay.
Yeah. Any other question? This. Okay. So now let's go to the second part. So the second part is derivation of h nu divided by e power h nu by k dt minus 1. Now, both in the work of Max Planck as well as in the work of this is always so the interpretation has always been that so in all previous derivations, I mean previous means up to Bose. This is calculated as an average energy of a dipole oscillator. But if we consider radiation as a thermodynamic system or as a system under study, we should be able to this without any reference to any material. Now, how do we do this? Now, the issue is you have to now devise a way of counting these things. Okay? That is, let's say that you have. So what is it that we have? We have certain oscillators. Sorry, we have radiation. So all that we have is we have radiation. What is called as some temperature radiation. Radiation at temperature. Now this radiation, we do not know whether this is a radiation from a black body called sun or a black body called Big Bang. What is the source of radiation? We don't know. So when we are considering radiation as a system, we don't have to worry about the source. And then there is no material oscillator that is under consideration. Okay. So you can ask a question. Okay. So first, let me tell you the simple answer to this from what we already know. So the simple answer is the following. The simple answer is the following. We have seen that the average number of photons, in this case particles are photons occupying, in this case of course means having energy h nu is so let me call that as some average n. Now this is something which we have already seen in our previous analysis of Bose-Einstein statistics. This is given by 1 by e to the power beta, the energy is h nu minus 1. Okay. Why this is correct? Since mu is equal to 0 for photons, because these photons are massless and they can be annihilated and created. They can be annihilated or created with no cost of energy. Okay. So chemical potential is 0. That implies the fugacity is equal to 1. So otherwise z to the minus 1 was there. So that is not good. So now you can ask a question. That means remember that you are going to, so this is like a state, right? So a nu or a particular P is associated with a particular cell. So that means this N is like average number of photons in a cell. And where is that cell? That cell is there with a momentum h nu by c. So this is the average number of photons in a cell. Okay. Now you can ask a question that what is the average energy? Average energy is basically average number of photons in that cell multiplied by h nu. That is given by h nu divided by e to the power beta h nu minus 1. So this is that factor. Now you can see that I have no material oscillator used anywhere. Okay, I'm only talking about what is the average number of particles, average number of particles in that cell, and then what is the energy of that cell. Energy of the cell is given by h nu, and average number times the energy of the cell gives you the average energy. Okay, so this is the answer. I called it simple answer because I am trying to derive this answer from whatever we have discussed about the Bose-Einstein condensation, Bose-Einstein statistics. So this formula is what we have already derived in the last class and used it in Bose-Einstein statistics. So I have taken this formula as such. And then this is the, now the thing is that is this how Bose derived? Answer is no, because we have used certain things that we have discussed in a formal way. So now we ask a question: what kind of technique that was used? Now to understand this, we have to understand something about the counting that has been done in classical statistical mechanics. Okay, so let us discuss a little bit about counting. Okay, so some discussion on counting in classical statistical mechanics. Now, as you know that if you have some n particles, let's say you have n particles, and let's say you have if these particles are, let's say, distinguishable, let's say they are distinguishable, then let's say that you have some kind of a partition function z, and what happens if they are indistinguishable? Then you will say that the partition function is z divided by factorial. This is what we have discussed during our study of Gibbs paradox. Now let's try to understand this n factorial little carefully. Supposing, let's say that we have, so consider some simple examples. For example, let's say first example, let's say that we have two particles in three states. Okay, and energy of all the three states is equal to 0. That means they are degenerate states. Now we can ask a question that because energy is 0, e to the minus beta epsilon is 1, so the partition function is same as the number of microstates. Okay, so we ask how many possible microstates are there. Since it is 2 and 3, I can explicitly write it in the following fashion. Suppose, let's say first we say they are distinguishable. Okay, then I have let's say 3 states. These particles are A, B. They can be in this state, They can be in this state. Like this. So it can be A, it can be B, or it can be B and it can be A. So this can be A and this can be B. This can be B and this can be A. And this can be B. And lastly, this can be B and this can be A. So the total number of microstates, if you see, there are 6 of them here and 3 of them there. So if you ask what is the partition function, we say that the partition function is going to be equal to 9. Okay, this is the partition. Now suddenly you make
So it was the number of microstate.
Correct, because each one is epsilon equal to 0. The number of microstates is same as the partition function, because e to the minus beta epsilon is 1 for everything. No?
Yes, sir.
So like that, it is just number of microstates.
Okay, sir.
So now let us make these particles indistinguishable. Okay, so the moment you make this indistinguishable, you will see that these particles, this is, let's say, AA, and this is AA, and this is AA. And now these two things you cannot distinguish. So you are going to have one state corresponding to this, and these two cannot be distinguished. So you have A, and then these two cannot be distinguished. So you have A. So if you look at this, this is equal to, so let us call this as Z distinguishable and Z indistinguishable. This is equal to 6. But this is not equal to Z distinguishable by 2 factorial. As you can see, it is not even an integer. Okay, so notice that this, so one has to see that this division by factorial n to get Z indistinguishable from Z distinguishable is only correct for large n, in which case this becomes linear and this becomes this kind of states become very large and these kind of states become small, and hence you can say that this is probably a correct thing only in very large n limit. Okay, this is one aspect. Now the second aspect is that, so this is one thing, and the second thing is that when you consider this, so when you consider the ideal gas, okay, so for ideal gas, for classical ideal gas, we have used 1 by n factorial. Okay, we have written our Z to be equal to 1 by n factorial into 1 by h power 3n into integral e to the power minus beta h q bar t bar into dq bar dq bar. This is how we have written our partition function. So notice that we have used this. Okay, so notice that these atoms are treated indistinguishable. On the other hand, for a set of harmonic oscillators, we had written down that this Z is equal to 1 over h to the power 3n integral e to the minus beta h of q bar p bar into dq bar dt. Okay, so here no n factorial is used in the denominator because each oscillator can be distinguished from others by and the Hamiltonian depends on the position. True, of course, it's true. It's potential energy, namely I is equal to 1 to 3n half m omega square qi square. True, its potential energy. Now, I must tell you that during the time when people were trying to do statistical mechanics of various problems, that what problems require this n factorial uh, to be used in the denominator and what problems do not require this to be used, there seems to be a kind of a confusion. Okay. So it is not clear. Okay, so it is not clear when to use or when to divide by factorial n and when not. In fact, there is somebody wrote that this dividing by factorial n was perceived as some kind of thorn in the flesh This was the idiom that was used in the sense that imagine if you have a thorn in the flesh, how discomfort you will have. That means how much discomfort is there. So that is the kind of discomfort which people had with respect to using this factorial n. That means if you divide also, you don't know why you have divided. So you're always uncomfortable. Okay, so this is the kind of reality that was our understanding now is something more refined, but this is the time I'm talking about, times of work of Bose and Einstein. So I think the counting technique which Bose has introduced. Okay, so the counting technique was used does not require consideration of n factorial. And perhaps Einstein, historians say that Einstein was impressed by this because now this thorn can be removed. Okay, so Einstein called it in his called it a novel counting procedure. That's what I think he called in his translator's note. To Bose paper. And I think we should also a little bit see that something like 4th June 1924 is what Bose sends his paper to Einstein. Okay, and during that time there are no, it has to go through C-mail, remember. And 2nd July 1924, Einstein replies. That means before that itself he has translated and sent it to that German journal, Zeitschrift for Physik journal. And then 10th July 1924, Einstein writes a paper applying this counting technique to massive particles. That means particles with non-zero mass. So it is so quick and fast. So this is kind of a part of that history. Now we can ask so this particular, and also I want you to recall that when we discussed this grand canonical partition function and grand canonical ensemble, and when we were talking about this what is called the occupation number representation, so I told you that there is no So now suppose, okay, so now let us look at, suppose let's say I have a cell. Okay, so let us call this is my phase space cell. Phase space cell. Okay, now what is the energy of this cell? Energy. So if there is one photon in this cell, okay, so let's say there is one photon, or let's call this as number of photons, or photon number. Suppose if there is only one, there is no photon, then the energy is 0. If there is one photon, then the energy is h nu. If there are two photons, then the energy is 2 h nu. If there are three photons, then the energy is 3 h nu, and so on. Correct? If there is one photon or two photons or three photons, depending on that, there is an energy like this. Now, this is, each one of this is like as far. Now, forget about the rest of the space. If I'm just looking at this cell alone, okay. If I'm looking at this cell alone, then this cell may have an energy 0, or it may have an energy h nu. It may have an energy 2 h nu. It may have an energy 3 h nu. So it is like this particular energy state can have a particle, one particle or two particle or zero particle, etc. It can have infinitely many particles also. So one can ask a question. Suppose if you are simply thinking that I have epsilon 1 is equal to 0 and epsilon 2 is equal to h nu and so on, or epsilon 0 is equal to 0, epsilon 1 is equal to h nu, etc. Epsilon n is equal to n h nu. And then you simply want to write down what is your partition function, then this is going to be e to the power minus beta into n h nu from n is equal to 0 to infinity. Correct? If I am just looking at this cell alone. Okay. Then this means what? This means this is equal to this is like a geometric series 1 by 1 minus e to the minus beta h nu. Correct? Then you have, so once you know this, then you can write down what is the average energy of the cell is minus dou by dou beta of logarithm of z, which gives you h nu divided by e to the beta h nu minus 1. Now, you have to understand this shift in the language that we have been talking. So if you look at Bose's work in 1924 and before Bose, okay, so this is before Bose. Before Bose, you have something like the statistics was something like a particle centric. I would like to, this is my language, but I would like to call it as particle centric. That means we are calculating number of particles, average number of that is partition function for the particle, partition function for the particles, average energy of the particle, and so on. But after Bose, see, this is the average energy of what? So this is whose average energy? Okay, we have written down this this one, but it's not average energy of photon, because photon has an energy h nu. That's all. But whose average energy is this? This is the average energy of this phase space cell. That means we have something called, after Bose, we have what is called state-centric statistics. State-centric.
Can you repeat that? What you said? Average energy of what? So?
This is not average energy of the particle. This is the average energy of this phase space cell. Okay, we are talking about a particular phase space cell. And what is the average energy of that phase space cell? And as I told you, that phase space cell is same as the state, as the energy eigenstate. Later, we call this energy state. So we are now shifting from particle centric to state centric. So we are now going, whose average energy it is? It is the average energy of the phase space cell. And this average energy is important because this average energy is coming because of average number of particles. Otherwise, if you say that you have got phase space, let's say that you have let's say that I have a phase space. Let's say I have some Q and P here, Q bar and P bar, whatever. So let's say I have a point here and I have a cell here. Okay. So now, so the nu of this is fixed. Nu is fixed. Okay. So the momentum of this one is simply h nu by c, that is fixed. The energy is h nu, that is also fixed. But then why there is an average energy? Because as far as this cell is concerned, even though that cell has got a particular frequency, but there can be more number of particles that can have the same frequency, which means they can be there in that cell. Because of this number that is getting fluctuated, there is an average energy of this. It is basically the average energy is derived from the average n. Okay, so this is the particle, what I am calling as state-centric. Okay, so this is derived from this because this n is now the point is that I want you to appreciate that this kind of a picture it has an idea which is yet to come, in the sense that this kind of a thing is this kind of a picture is in some sense is an indicative, or I would say that it is because of the identical nature of the particles is at the heart of this shift in statistics. Okay. So maybe I have I'm not sure how clear it is, but it will be good if I can demonstrate it more clearly. But let me see if I can do that. But at this moment, I want you to appreciate that if these are not identical, then this kind of a simplified measure of average energy without having any reference to the oscillator is not possible. Okay, so even though in Bose paper he did not say these are identical or anything, but I think his way of deriving this assumes or considers them to be identical, which later, when we understand identical particles in quantum mechanics, it is clear that it is because of the wave function overlap that we have this identical nature come so forcefully that we have different types of statistics. And what Bose has done is what we now call as Bose-Einstein statistics. Okay. So this is with respect to the work on black body radiation, and we have, as I told you, that there are two issues. One is with respect to deriving 8 pi nu square by c cube, and the other is deriving this h nu by e to the h nu by kb minus 1. And in both cases, he has used his own style of deriving this. And in both the cases, he completely assumed the quantum nature of the light quanta and then developed theory by totally believing that this photon, the light is a particle. In the previous derivation, there was a half-hearted belief that some people believe, okay, some parts of it they used as particle nature, but some part of it they used as wave nature. But Bose, for once, have believed that it is completely a particle, and then applied this statistics to a set of particles, and then had given rise to this formula by completely assuming that it is the particle. And this, for once, the identical nature of the particle is what gives rise to removal of this n factorial. So I want you to recall that when we use this grand canonical partition function, we have grand canonical partition function. We had written down that this n is equal to 0 to infinity, z to the power n, and you have come over this ni with a constraint that sum over I ni is equal to total n into e to the minus beta into sum over j nj into epsilon. So when we had this for Bose-Einstein condensation, we have written this as sum over nj is equal to 0 to infinity, or simply I will write this as sum over nj at this moment. So let us write this as product over j and sum over nj into z e to the minus beta epsilon j to the power nj. Now, from here we have written for Fermi-Dirac statistics, your nj will take only 0, 1, and for Bose-Einstein statistics, nj will take 0, 1, 2, etc. up to infinity. On the other hand, for Maxwell-Goldman statistics, we had written this Q to be this n is equal to 0 to infinity, z to the power n, and sum over n I and I have a factor here. The factor is n factorial divided by n0 factorial, n1 factorial, etc., etc., etc. And then there is a 1 by n factorial, that is to take care of the indistinguishability. And then you have e to the minus beta and sum over J, Nj, epsilon. Okay, so only when we have this one, you can write this as product over J, sum over Nj, that is equal to 0 to infinity. I have Z e to the minus beta epsilon j to the power nj divided by factorial n. So then this can be written as sum over product over j into exponential of z into e to the minus beta epsilon. Okay, so this factor and this factor is not required for Bose, Einstein, and Fermi-Dirac statistics. That is because of the identical nature of these particles. And that is what I think precisely Einstein had appreciated from the counting technique of Bose. And then he immediately realized that if you apply to this Bose, the integral spin particles of finite mass, then there is Bose-Einstein condensation. Okay, I think a year later, Einstein wrote a paper in which he worked out Bose-Einstein condensation, and then showed that it is a consequence of this new statistics that Bose has introduced, that you have a new state of matter in which all the particles will go to the ground state. Okay, so I will stop here. If there are questions, we can discuss. Any questions? Okay, thank you for giving me time. Because of that cyclone, we were not able to do the class on Wednesday.
Sir, one small doubt, sir.
Yeah.
Sir, doubt in two-level system.
Yeah.
For the two-level system, when we fix n, we have different values for energy, right, sir? For example, you fixed n as 3. And we wrote energy to be 3 epsilon, minus 3 epsilon. But that two-level system was solved using microcanonical ensemble.
Okay.
Their entropy was a function of energy, no, sir. And now energy is discrete, no, sir. Then how do we take a partial derivative of entropy with respect to energy?
No, whenever we are taking okay, so I mean, if I understand what you are asking. So what you are saying is that if you have a two-level system, this with energy minus epsilon and this with energy epsilon, right?
Correct.
Okay. So if you have totally n number of particles, then your total energy can be between minus n epsilon and plus n epsilon. Correct? Because all the particles can be in the ground state or all the particles can be in the excited state. Correct? So this is your energy. But what you are saying is that it is minus n epsilon, and then there is a gap, and then there is some energy like that. These are discrete.
Yes, sir. If that's the case,
So energy is discrete. Okay. So now we are asking, when you take S as a function of energy,
and to do
how do we take
thermodynamics,
Bose to do?
because we need to do thermodynamics.
Yeah. So this is the question, right? How do you take partial derivative of S with respect to energy? Yeah. So most of these questions are somehow masked by this fact that we are doing this in thermodynamic limit. Okay, so what happens in thermodynamic limit is that this particular epsilon is itself is much smaller than this energy. Okay, so epsilon is much smaller than this energy, and this discrete nature. Okay, so discrete that is energy space, what you call as. Okay, are you reading? Are you seeing what I am writing?
Yes, sir. Yes, sir. Able to see.
Okay. So energy space is of the order of epsilon, and in thermodynamic limit, what happens is that epsilon or E epsilon divided by E is almost goes to 0. So one can assume some kind of a continuum. Okay. So in that sense, you can take this derivative.
Okay, so
Because n is going in this limit, what happens is this n becomes infinity, right? So as n goes to infinity, you have a very huge energy. Total energy is very large, and compared to that, epsilon is very small.
okay, sir. But in microcanonical ensemble, we'll fix E no, sir. We'll fix E no, sir. E can be lesser. I mean, E can be
Correct.
chosen to be.
Yeah. So when you do calculation for a fixed n and fixed e, okay, but then they are large. Okay, they themselves, whatever we are fixing, are large. We are simply saying some n and some e. You must make them very large.
Okay, sir.
Okay, so E is very large such that epsilon is very small compared to that. Okay, that is the argument.
Okay, sir.
Sir,
Yeah.
insurance